We offer several MolCube workflows including system build, docking, and alchemical free energy simulator. Today we will introduce the membrane workflow. On the left side of the panel below, locate the MolCube workflow and click Quick Start. All workflow processes are displayed on the dashboard. Select Membrane and click Start. You will find information about Membrane System Builder. Before starting the workflow, please review this information for a better experience. Once you've reviewed the information, click Start. The workflow will begin, and you'll be prompted to enter the project title. Workflows may include multiple projects. Therefore, you can distinguish between the workflow title and the project title. After entering the project title, click Create. Next, we move to the PDB reader step. We enter the desired title for this demonstration. We use 7Y9B and click Submit. In Step 2, enter the PDB ID or UniProt ID of the protein you want to use. If you are using a custom file, you can upload it directly or load a predicted structure generated from bolts, to, or Protonix. After adding any necessary options, click Submit. After submission, the next step will be prepared automatically. In Step 3, the structure for 7Y9B appears. We use 7Y9B because it's the crystal structure of the membrane protein from a SARS-CoV-2-related coronavirus, which makes it suitable to demonstrate a membrane protein workflow. On chain selection, we keep Prot A and Prot B, and we deselect Prot C and Prot D. This keeps a representative dimer interface while removing redundant symmetry mates, reducing system size and compute cost for the demo. Under standalone ligands, we add the listed co-resolved ligand, for example N8E. We click Validate Structure, then Apply, so that local packing around the protein is preserved. We'll leave all other options at their default values. Click Submit and go to the final step of PDB Reader. In Step 5, check the generated structure and click Go to Next Step. We're now in Membrane Builder. First, in Search for Project, we select the 7Y9B PDB reader entry we just prepared. Under Membrane Type, we choose Bilayer, since we're embedding a membrane protein. For box shape, we select rectangular to use an orthogonal box. For the force field, we choose Charm FF, and it's important that this matches the force field we used in PDB Reader. After that, click Submit. Let's go to Alignment. We see three options: As Is, Principal Axis, and PPM. For a robust orientation of the transmembrane region, we choose PPM, which follows OPM standards. Then we click Submit. Step 3 is lipid composition. We could enter specific lipid species and mole fractions manually, but for this demo we'll select a predefined biomembrane. We choose PMM and click Apply. The lipid types and ratios are populated automatically. After reviewing the composition, click Submit. In Step 4, you can view the fully packed lipid composition. After reviewing the results, click Submit to proceed to the next step. Now we configure the environment. Here we set the water thickness above and below the bilayer, define the hydration number, that's waters per lipid, decide whether to neutralize only or add a specific ion concentration, and set the temperature in Kelvin. We can also enable hydrogen mass repartitioning to run with a 4Fem2 second time step. Finally, we select our MD engine. In this demonstration, we'll choose GROMAX and then click Submit. At the review step, we see a full 3D visualization of the system alongside system info, component ratios, total atom counts, net charge, and an energy breakdown. If everything looks correct, we click Download to retrieve the generated PDB GROTOP XML or simply download the entire project bundle. Then we click Next to proceed. Now we are on the membrane simulator. The default runtime is 10 nanoseconds, extendable to 100 nanoseconds. Confirm the MD engine and click Submit to start the run. The running 7Y9B project appears at the top. Completed runs are labeled Step 4.4. Although you can download the finished trajectories and analyze them externally, the workflow also provides built-in analysis modules you can launch immediately. To analyze the simulation results, click Resum on the dashboard and then select Membrane Analyzer Step 1. The Membrane Analyzer provides 20 analysis methods. In this demo, we select membrane centering and system dimensions, starting with membrane centering. For clarity in selections, we label the membrane as segment ID MEMB and the solvent and ions as segment ID SOLV and IONS. Membrane centering is performed in 2 steps. First, the system box center is aligned with the origin, and the membrane is wrapped by fragments under periodic boundary conditions. Then, the bilayer is fine-centered using its center of mass, and the solvent is wrapped at the residue level. This 2-step process ensures that the bilayer symmetry is preserved and that the membrane remains intact even when it crosses the box boundaries. Now we move on to system dimensions. Here we specify the time range for the analysis, for example from the start of the production run, 0 nanoseconds, to an end time such as 100 nanoseconds, and click Run on AWS and Submit. When the analysis finishes, the dashboard highlights Step 4 in green. Clicking Resum brings up the results, where we can see time series values of the system's X, Y, and Z box lengths in angstroms. All data and figures can be downloaded for further use. With this, we complete the demonstration of the end-to-end membrane workflow, showing how a system can be built, simulated, and analyzed with just a few clicks.